at the current slide. And I don't know if this is of any interest to you, because you're a transient student, right? You're not. Okay. I think I announced this before, did I? About STEM jobs. Yeah, STEM jobs. Okay. If you're interested in seeing that, I've got it up here. I've announced all my classes. Anyone is free, welcome to take it if you want to. Just in case anyone shows up that wasn't here for the earlier announcement, I'll do it again. Okay, any questions on differential equation stuff? Okay. All right, and you did, saw you had the test for the second one, okay. And we aren't doing chapter 3 unless we have time at the end, which is not very likely. So we've gone on to chapter 4, which is higher order differential equations. And I just barely got started on this last time when I ran out of time. So we're at the top of page 119 if you've got a text. And this is also for people listening at home. And it's basically, this section, 4.1, is preliminary theory linear equations, okay? In the other sections, we're going to talk about higher order differential equations that are not linear. The linears are generally the easier ones, so to speak. Okay, there was a comment, actually they call them remarks at the end of section 1.1 and page 57 of section 2.3, when they talked about general solution as opposed to a specific solution. Recall that a general solution is a family of solutions defined on some interval I, okay, that contains all the solutions of that differential equation that are defined on I. Now that's usually done for non-initial value problems. When you set it up, you have nothing, then you'll have some constants of integration, right? C1, possibly C2, C3, whatever. Those will define your family of solutions. Okay. So 4.1.1 is now not talking about the general, but we're going to hit the general first. The initial value and boundary value problems. I think I've mentioned boundary value before. So let's hit initial value problem in terms of higher order differential equations. Section 1.2, we did initial value problems for a general nth order differential equation. And let's review that for just a moment here. For a linear differential equation of nth order initial value problem, IVP, here's how it looks. A sub n. Now that n there is just a marker. That's just saying this is the coefficient A that goes with the term whose degree is n. So this is A sub n of x. And I'll get to that in just a second. D n y dx to the n. Now, I may have said degree. I meant to say whose derivative is the nth derivative. Okay? Plus, and again, a sub n minus 1, indicating that's the coefficient function of x that goes with the n minus first derivative. Okay, and by the way, well, no, this is okay in this one. Plus, and we got count on down, a sub n minus 2 of x d to the n minus 2, this n minus second derivative of y with respect to x that many times. Whoops, I didn't put the 1 there. Okay, plus I'll put dot, dot, dot for a while there. Plus, and then we'll pick up at the other end, I'll put a sub 3 of x d, the third derivative of y with respect to x cubed, plus a sub 2 x, the second derivative of y with respect to x squared, plus a sub 1 of x dy dx, plus a sub 0 of x, okay, and that's equal to some g of x. Now, I'm sorry, I left off the y. Okay. Now, that's the general form for a linear nth order differential equation in x, one variable. Okay? Now, what makes it linear? Okay? The fact that every one of these y's you see here and derivatives of y are to the first and only to the first power. Okay? This is not the third derivative of y squared. Not that. Okay? It can't be that anywhere, or to the seventh power or anything else. Nor can there be any cross products with y's. Like this could be a sub n of x, y d. You can't have a y or fourth derivative in here or anything else. The only place y shows up is in its derivative or in the function, and there it's only to the first power, and there's only one of them per term. Now, all the coefficients here are actually coefficient functions of x, but x alone, because if you had a y in there, then y's would be mixed up with the derivatives. Okay? So that's what makes it linear, and the fact that the constant function over here is a function of x alone. Not say a constant function. The function over there is a function of x alone, just like each one of these coefficient functions are. Now, they don't have to have an x dependence, but they can. That's an nth order linear differential equation. Okay? That's how they look. Now, if you had one of these and it was an initial value problem, you have to have an initial condition for every one of these things, these derivatives and function, up to but not including the last one. Okay? The nth derivative. But all the rest of them you need, so therefore your initial values subject to y of x0 is equal to y0, y of x0, y prime of x0 is equal to y1. Make sure that's the same thing there. Yeah. Y double prime at x0 is equal to y2. I'll do a dot, dot, dot here. Y, the n minus second derivative of y of x0 is equal to y of n minus 2. Now, here you have to be a little more careful. I thought this, okay. Just a little nitpicky thing. When you're expressing in derivatives in, what was the guy's name? Not the other guy, German guy. Why am I going blank on that? Gottlieb, the Leibniz notation. You don't need to put that n minus 1 in parentheses, because that's obviously a derivative. When you're doing it in prime notation, you have to put that in parentheses. If you don't, you think of that as a power, not a derivative. So that has to be in parentheses there, where it doesn't up above. Okay? Comma, y sub n minus, the n minus first derivative of y at x0 is y of n minus 1, and stop there. Okay? You don't do the last one. You don't do the nth. Okay? And by the way, this is the nth derivative here, and you have, that means you have n derivatives, 1, 2, 3, 4, 5 derivatives, but you also have the function to the 0th derivative. In other words, that's a function. Well, how many conditions do you have? 0, 1, 2, 3, 4, 5, 6, 7, up to n minus 1, which is, because you have a 0 in here, n conditions. So if it's nth derivative here, you have n conditions down here. However, you don't have a condition for the nth derivative, because that would give you n minus 1. I mean, n plus 1 conditions, and you don't need those. Good to see you. Okay. pieces here. All right. We're on page, in Chapter 4, Higher Order Differential Equations, 4.1, Preliminary Theory, Linear Equations, 4.1.1, Initial Value and Boundary Value Problems. We just identified an initial value problem in a higher order, nth degree, differential equation. Nth order. Probably better say order. Degree makes you think powers. So nth order linear differential equation. That's your initial value problem. Now, back in section 1.2, we stated a theorem that gave conditions under which existence and uniqueness of a solution of a first order initial value problem were guaranteed. The theorem that follows gives sufficient conditions. The other was which the existence and uniqueness of a solution. This one gives the sufficient conditions for the existence of a unique solution. Okay? Just a minor second. Is page 119. Yeah. Kind of the second half of the page here. So here is that theorem, 4.1.1. Existence of a unique solution. Let these a sub n of x, a sub n minus 1 of x, a sub n minus 2 of x, dot, 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 down to and including a sub 3 of x, a sub 2 of x, a sub 1 of x, and a sub 0 of x. And do they include g? Yes. And g of x. Okay? All these are continuous. Okay? That has to be on some interval I. Okay? And a sub n of x cannot equal 0. Now that sounds a lot like your situation for nth order polynomials. And for the very same reason. Okay? If this were 0, that would not be an nth order differential equation. Because the first term would be 0. It would be an nth minus 1 degree. We're talking about nth order linear differential equation. So therefore, this a sub n of x cannot be 0. Any of the rest of them can be. That's perfectly fine. The g can be 0. Any of them can be 0 except that. Okay? It can't. Okay? Otherwise, it's not an nth order differential equation. Okay? And that's for every x in this interval. Okay? A sub n of x cannot be equal to 0 for every x in the interval. Okay, I've doubled that. Okay. If x is equal to x0, okay, if x equal to x0 is any point in the interval, okay, any point in that interval, then there is a solution okay, y of x, solution y of x of the IVP and this IVP is this whole thing up here, the equation and the conditions, okay, that exist on the interval and is unique. Okay, there is a solution. Okay, now again, let's see what is required. Every one of those functions of x, every one of them has to be continuous on that interval. Whatever interval this thing is defined on, every one of those has to be continuous. You can't have any piecewise defined that have jumps or gaps, missing values, or anything else like that. They have to be continuous. Now think about what that means. if any of these are rational expressions, then they cannot have a 0 in the denominator. If any of them are radical expressions, they can't have any x's for which, say, an even root is undefined. Okay? If it has a ln or a log anywhere in it, that the x can't be 0 or negative. So there can't be any discontinuities. Okay? They all have to be continuous. And of course, that one can't be 0. We already talked about that. For every x in that interval I. So if x equal x0, which is the point at which your initial condition is rest, it has to be also in that interval I. And as long as that's the case, then there will be a unique solution that it does exist and will be unique for that differential equation. Some y of x that works. Okay? So let's do example 1. Any questions on that before we go? A lot of blah, 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 but let's see what happens. Here is an initial value problem. Much simpler looking than what we just had. 3y triple prime plus 5y double prime minus y prime plus 7y is equal to 0. Okay. Now, things to note here. Every one of those a of x's has no x dependence. They're just constants, which is perfectly fine. Okay? Perfectly fine. And it's perfectly fine that Rod is here. Okay. Good deal. So good to see you people. I was selling curry earlier. Tuesday, 0 for 7. Okay, I was in there all by my little lonesome, and it was pretty boring. What y'all have to listen to, I had to listen to. Sorry about that. Okay, so this is a third order linear differential equation. For those who came in a little bit later, what makes this linear? All the y's and the derivatives of y's are to the first power, and you don't have any mixed things. Like you don't have a plus 5y double prime y prime, or a minus y prime squared, or plus 7y y triple prime. You can't have any of those. Each of these is not to any power and not with any cost products. That is what makes it linear. Okay? Now, we just did a theorem that said, okay, sorry, let's finish the problem. Okay, here's the problem. Y of 1 is equal to 0. Y prime of 1 is equal to 0. And guess what? Y double prime of 1 is equal to 0. Now, the fact those are all zeros has nothing to do with the problem here, okay? I wish they had done, picked a value, 1's perfectly fine, and then had other values for them. That would work just as well. The fact that these are all zeros doesn't make anything special happen, except it makes it easier to evaluate at the end, okay? Now, we've seen the last theorem, the one we just did before you came in, Rod, said that this, if each of these coefficient functions is continuous, they're all constants. They got to be continuous, right? And what's the second part? On the interval, which is all real numbers, they're continuous everywhere. And 1 is on that interval. That's the thing that you're evaluating at. That's on that interval. So this is going to have a unique solution. One and only one solution. Now, I want you to put on your thinking caps for a minute. Not that you ever have them off, but can you think of some function that function you can add or subtract something with its derivative, second derivative, third derivative, and you're guaranteed you can find some linear combination of that that's always going to be 0. Some function that worked. There you are. Good to see you. Okay. got to find you now. There's Lauren. Okay. All right. Some function that, let me put it this way. I can't think of a polynomial function, at least any degree greater than, no, I can't think of any polynomial function that when you take its derivatives, you're going to be able to combine just constant multiples of those things and get it to equal 0. Because if that has an x value somewhere in it, okay, at some power, this is going to be a lesser power, lesser power, lesser power. You'll never have anything with that original power, will you? Okay? I sure don't want to think of any rational functions that you can guarantee that will be the case. Can you think of any function, any kind of function that's similar enough to all of its derivatives that that's always going to be, that you could probably make that happen? Okay. You have just, if x is equal to 0, well, that's not a function. Now, if you had said y is equal to 0, that's certainly, all those things would be true there. But see, that's a unique, we need y to be a function of x, not just a single value. But y is equal to 0 certainly is going to make that work. And we said that's a unique value, so unfortunately you sort of hit one that would be. But that's a very special one, you know, that we usually exclude. So, but real good insight, okay? Any function, type of a function, that you can guarantee it and its derivatives up to the third derivative or higher, some combination of them, you can always get some linear combination to be 0. In other words, okay, y is equal to x minus 1. Okay, so this would have an x minus 1 right there. The first derivative of that would just be 1. Second derivative is 0, 0, 0. Okay, you'll never get rid of that x term. Okay, these go to 0. That's fine. That is excellent. But this doesn't have an x in it. That does. Can't make it equal to 0 for all values of x in that interval that you're choosing. What function, when you take its derivative, doesn't change very much at all? E function, the exponential function. Let's let that be our guess. Okay, now you're absolutely right. You hit it right on the nose. It possesses the trivial solution, y is equal to 0. Okay? And you hit it. You nailed it right there when you said that. That's the trivial solution. Because the third order equation is linear, constant coefficients, it follows that theorem is fulfilled. Therefore, not only was what I'm suggesting not work, it can't work. Because you're absolutely right. That is the only function. Remember we said unique? Because that works, it is. I was going to say we usually ignore the trivial solution. We really can't. Okay? We really can't ignore that trivial solution. That is the one and only one. So you nailed it right there. Good job. Okay? So let's go to example 2. Maybe this is the one I was thinking we were going to be doing. Okay? Here's an initial value problem. Y double prime minus 4y is equal to 12x. Okay? Subject to y of 0 is equal to 4. This time they don't have it. And by the way, let's back up a moment. I'm sorry I erased the other one. I was wrong in what I was saying. I said that the fact that they're all equal to 0, the y is equal to 0, the y prime is equal to 0, and y double prime is equal to 0. No, that meant that y equals 0 is the only solution. That's the only thing. If we had chosen e to the x, like I was suggesting when we tried, then you wouldn't have gotten zeros for all those. Because guess what? E to the x is never 0. Is it? It approaches 0 but never gets there. So I was wrong in saying that. That should have alerted me to the fact there's got to be y is equal to 0. But good job in seeing that. Okay? And it just dawned on me when I wrote this down. This one can't have the same situation. Okay? And here's Monica. Okay. Good attendance today, folks. Missing Taylor. You're Monica, right? Yeah, okay, I want to make sure I got it right. And missing Jasmine. Okay? And the reason I sort of said that way, Tuesday, 0 for 7. I was the only one here on Tuesday, so glad y'all are here today. It makes it so much more fun to teach. Okay? How many initial value situations do we need for a problem like this? Is that one enough? Yeah, we need 2 because it's a second order. So the second one, and it's got to be this, for initial value problem, y prime, and it has to be at the same value, 0, but it doesn't have to have the same value. In this case, it's 1. Now, I'll just say, if Curry were to guess again y is equal to 0, that's not going to work, okay, because that would be good if that was a 0 there and 0s everywhere else, but it's not going to work here, okay, because for any value x other than 0, that couldn't possibly be the case. Now, of course, y of 0 can't be 4 if y is equal to 0 everywhere. So, this is a separate situation. Now is where we will try something like this. Y is equal to e to the mx. Okay? That is going to be our guess. Well, no. We're not quite ready for that yet, because this one has that 12x there. You can't say that. So let me delete this. I was trying to do a little bit beyond what the book was doing, but I realized with that 12x in there we can't. It says you should verify that this function, okay, y is equal to 3e to the 2x plus e to the minus 2x minus 3x is a solution for that equation. Okay? So we're going back to verifying. Remember the first chapter, that's all we did was verify. So how would you verify that to be the case? What's the first thing you're going to have to do? Take a derivative. Y prime is equal to 6e to the 2x minus 2e to the minus 2x minus 3. But really that y prime doesn't do us a lot of good because there's no y prime in the problem. But we got to have it in order to get y double prime. And what would y double prime be? 12e to the 2x plus 4e to the minus 2x, done. Okay? So there's what we need. Let's plug these things back in here. So that would be 12e to the 2x plus 4e to the minus 2x minus 4 times our y, well, here's the y, 3e to the 2x plus e to the minus 2x minus 3x, all that is your y, okay? And the question is this equal to 12x? Okay, well, let's see. This is 12e to the 2x plus 4e to the minus 2x minus 12e to the 2x. It's good so far. Minus 4e to the minus 2x. Really good so far. Plus 12x. And sure enough, that is equal to 12x. because this one and that one add to 0, this one and this one add to 0. Sure enough, 12x is equal to 12x. Are we through? Verifying? Not really. We also have to make sure that y of 0, when x is 0, what is e to the 0? 1. So that would be 3 plus 1 plus 0, or minus 0. 3 plus 1 is 4. Yep, that works. And y prime, this will be 6, which is minus 3 is 1. Yes, that one works too. So both of our initial conditions work. It's not enough to just show that the equation works. You also have to show that the initial conditions are met too. And they were. So sure enough, we have verified that. Okay? Now, knowing that, and the theorem we did earlier, these are continuous functions. 1, minus 4, and 12x are continuous functions everywhere. This is a unique solution for all real numbers x. Okay? And I, they don't even mention I that I can see anywhere. It says on any interval I that contains x equals 0. Now, why would they throw that little caveat in there? Is there any reason that the interval has to, oh, of course it does. Why does it have to contain 0? That is the value you got for your initial condition, x is 0. So you can have an interval that doesn't contain 0 and those conditions be met because of that. Pretty obvious, sorry. Okay. 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 They say, all right. Let's see here is another function. I'm going to erase all this. I was trying to see if this was worth the time. I think it probably is. Here's the differential equations. X squared y double prime minus 2x y prime plus 2 y equals 6. Okay? Is that a linear second order differential equation? Yes. Are those functions, x squared, 2x, minus 2x, 2, and 6, all continuous functions? Yes. Okay? Here's the kicker, though. Is x squared continuous everywhere? Oh, wait. It's continuous everywhere, yes. Is it non-zero everywhere? No. Where would it be equal to 0? At x equals 0. So therefore, bells should ring, lights should flash, and say, wait a minute, this will not be true on an interval which contains x equals 0. Can't. 1 to 17, no problem. -3 to -2, no problem, okay? But you can't be -2 to positive 1. That would contain 0, okay? Well, let's see. I've lost it. There it is. Okay. Here are the initial conditions. Lost them again. There they are. Y of 0 is equal to 3. And y prime of 0 is equal to 1. Okay? Again, they look like a perfectly well set up linear first order differential equation, initial value problem, the differential equation here, all the functions are continuous. Your y's, you have your two initial conditions, the y and y prime for a second order, you need two. Looks like everything's fine, except for this. What are your initial conditions? Where are they? At x equals 0. And your coefficient here would be 0, x equals 0. So this is set up for disaster, folks. You know, either, I mean, it looks like it's going to be perfectly fine until you do this. Okay? So it says here, if I can find it again, verify that this solution, y is equal to cx squared plus x plus 3 is a solution for that problem. Now, what seems a little wrong with that being a solution for the problem? Well, if we have two initial conditions, we shouldn't have a parameter in there, should we? Well, let's see. Let's just see what happens. What do we have to do? Second? And what do you mean by that? Yeah, okay, I was hoping that's what you meant by it. Okay, and that would be what? Okay, and once more? 2c, or not 2c, okay. And that is a 6 there, not a c, okay. I do have it right, don't I? Yeah, okay. All right, let's go and plug back in. This will be a x squared, 2cx squared when you plug this in there, minus 2 x times 2cx plus 1 when you plug this in there, right? Plus 2 times this thing here, plugged in there, 2cx squared plus x plus 3. Okay, let's see what that gives us. 2cx squared minus 4, 2 times 2 is 4, cx squared minus 2x plus 2cx squared plus 2x plus 6. Is that equal to 6? Well, here's a 2cx squared, another 2cx squared, that makes 4 of them. There's a minus 4 2cx squared. There's a minus 2x, a plus 2x. Sure enough, that's equal to 6. 6 is equal to 6. That part works. Doesn't work if we plug in those values. When we plug in x equals 0, that goes to 0, that goes to 0. You have y is equal to 3. Yes. And when you plug in, I'm sorry. Yeah, I did the right one. And when you plug in x equals 0 here, y prime is equal to 1. Perfect! Perfect. It works perfectly. Except for the fact, why does it have a parameter in there? Okay? You have two conditions. You shouldn't have any arbitrary parameters in there. Okay? And it says, so that's not a unique solution, is it? You could choose any value c you wanted to. C is equal to 0, c is equal to 17, c is equal to minus 5/3. Doesn't matter. Any c you put in there, that would be a solution. Therefore, it violates our original thing. That should produce a unique solution. Or does it? Doesn't violate it because you didn't meet the conditions. It contains 0 on the interval, okay? And 0 on the interval makes that first term 0. And it can't happen. But 0 has to be in it because that's where you evaluate. So therefore, it looks like this is not a unique solution. And it's not, because you don't meet the criterion of the original theorem. Okay. Now, another type of problem. Any questions on that? They really major on some minors here, but it's something important you need to watch out for. Okay? A boundary value problem. Okay? Another type of problem consists of solving a linear differential equation of order 2 or greater in which the dependent variable y or its derivatives are specified at different points, not the same point. Remember, for an initial value problem, it doesn't have to be 0 always. It can be any value. Y of negative 17 is this, and y prime at negative 17 is that, and y double prime at negative 17. You just have to have the same value for all your function and your derivatives, all your conditions. A boundary value problem puts conditions at different points. Okay, here's an example. A2 of x, that's a function of x, d squared y, second derivative of y with respect to x squared, plus a1x dy dx, plus a0 of x y is equal to g of x. Okay? Now, if this was subject to this, y at value a is equal to some value y0, but y at some other value b is equal to y1. Or even y0. It doesn't matter. It doesn't have to be a different number, but it's just some value, some constant. Okay? That is not an initial value problem because the a and the b obviously are different values. If they're the same value, this doesn't even make sense. Okay? In other words, if this is y of 1 is equal to one value, and y of 1 is equal to some other value, that's not a function. Okay? So hang that one up. So this is different values a and b and different values y. That's fine, but that gives you a boundary value problem. And that's a BVP, boundary value problem. Okay? Now, and those are called the boundary conditions, by the way. Now, is that all this made up, or is there some real practical application for it? Do any of you play, say, a guitar? No, none of you do that. I don't either. Okay? But you've seen someone play a guitar, right? Okay? They put their finger here, and that fixes it on this fret, right? And it's fixed at this end. They pluck the string, and they get a certain frequency, right? A certain note. Do a different fret, a different note. Well, there you have your boundary conditions are fixed, okay, at different places, and that makes the sound different, okay? You have lots of things in physics and real life that are like this. You fix 2 points, and then you see what comes out of that, okay? It's just a real simple example, okay? A solution to this foregoing problem is a function satisfying the differential equation on some interval I containing a and b, both a and b have to be on that interval I, whose graph passes through the 2 points a, y1, y0, and b, y1. Got to, okay? And there are other boundary conditions you could have. I'm going to list a few of them here. They list, I think, for a second order differential equation, you could have also had y prime at a is equal to, say, that y0, and y of b is equal to that y1, or you could have had y of a is equal to y0, but y prime of b is equal to y1, or you could have had y prime of a is equal to y0, and y prime of b is equal to the y1. Okay? So it doesn't have to be a unique thing that they don't have to both be first power, or even one first and one second. They can do both first and I'll say power. Order, okay? Or they can both be first order. It doesn't matter, okay? But if you might guess, if all these are allowable boundary values or boundary conditions for you, you may wind up with a multiple number of solutions. And indeed, you do, okay? And we'll show that next. Here are the general boundary conditions that involve all those. Now, this gets to be a little bizarre, but it's true. Alpha 1 y times y of a, this is, I'm trying to get it to look the same as the one in the book. I like to put a parenthesis there, they don't. Y of a plus beta 1 y prime of a equals some gamma 1, and alpha 2 y of b plus beta 2 y prime at b is equal to some gamma 2. And I put this first one in the wrong place. These are subs, not supers. Okay. And basically what that tells you, to uniquely identify this, you actually need 6 conditions. That doesn't seem like it's reasonably true, but that's what they're saying, that you need 2 points, A and B, your boundary conditions, but then you can have these possibilities for your constants. And of course, you know, if 2 of them are fixed, the other one's fixed. So they're not completely independent of each other. Okay. I don't know really why they gave you that at this point. You don't need to know it, but they just gave it to you. So let's do example 3. Okay. They mentioned back in example 9 of section 1.1, we saw that the 2 parameter of solutions of this differential equation is this. So here's the differential equation, x double prime plus 16x is equal to 0. Okay? And a solution, 2 parameter family of solutions would be x equals c1 cosine 4t plus c2 sine 4t. Okay. That would be a solution. I don't know if you remember that, but we did it. Okay? Now, I'm sorry, my throat's clogging up on me. Most of the time we have y's being primed. This one has x's. That means you have a different independent variable. Not always, but most of the time that will be true. You know, this is classic physics type problem. In fact, this is a wave equation is what it turns out being. And usually that is time dependent. T doesn't have to represent time either, but you know, quite often when you see something other than y as your dependent variable, you can almost guarantee t or something like that will be your independent variable. Okay. Could have x as a function of y, but most of the time they don't do that. Okay. So this looks bizarre, but it's true. Now, that's just the differential equation with a 2-parameter solution. So let's say, suppose we now wish to determine the solution of the equation that further satisfies the boundary values, boundary conditions of this. This will go with the differential equation. That x of 0 is equal to 0. Okay, good. And the x of pi halves is also equal to 0. That's fine. Okay? Doesn't have to be the same equal, but it is in this case. Now, sorry. Okay. Let's plug in that first condition here, x equals, t is equal to 0. So we have x is equal to C1 cosine 4 times 0, which will just be 0, plus C2 sine 0. Okay, I can't write. I don't know what's going on. Let me clean those up a little bit. They're really, really ugly. Those are the numbers 0. They're not phis or thetas or anything else. That's cosine 0, sine 0. Well, what is cosine 0? 1. Okay. Oh, yeah. So that would be x equals C1, and what sine 0? Is 0. So you lost your C2. But that, when t is equal to 0, x has to be 0. So this implies that C1 is equal to 0, right? Well, what does the second one imply? X of t equal pi halves. Let me write it this way so it'll be easier to think through. That would be C1 cosine 4 times pi halves would be 4 times pi halves. Second? 2 pi, okay. Plus C2 times the sine of 2 pi, okay. When you plug that in there, again, what is cosine of 2 pi? 1. Sine of 2 pi? 0. So that says, and that this is equal to 0, that says C1 is equal to 0 again. Well, we already knew that, okay? So, your function then would just be x is equal to C2 sine 4t. And guess what? Even though you used your two conditions, boundary conditions, you still didn't eliminate but one of your parameters. So you still have a one-parameter system. This has an infinite number of solutions. Any C2 you want to put in there is going to make that work for that differential equation and those boundary conditions. So you haven't limited. You do not have a unique solution. That theorem we did, that was for initial value problems, not boundary value problems. This is not a unique solution. It depends on that particular set of boundary values still leave you a one-parameter system. Okay. Now, what if they gave you, so I'm going to erase parts of this. There we still have infinite number of solutions. So let's erase this. Actually, what is wrong with this thing? Okay. All right. This time we're going to have different boundary. Right. Same function. Here are the boundary values. X of 0, 0, same as before, and x of pi eighths equal to 0. Okay? All right? And that's your proposed solution. Oh, let me go and erase this one too. Okay? That was your solution that we got before. If you go back, plug in, everything works, except for the boundary values. Let's see what happens there. When you put in a 0, you've got this, C1 equals 0. That works same as before, right? But this time we'll do x equal C1 cosine, and what is 4 times pi eighths? Pi over 2, plus C2 sine pi over 2. Okay, let's see what we get there. What is cosine pi over 2? 0. Sine pi over 2? 1. So now we get C2 is equal to 0. Okay? Well, for that boundary condition to work, x equals 0 is your only solution. Not very exciting solution, isn't it? In other words, there is no solution for that problem. X is always equal to 0. That's the only solution you have. So it's a unique solution. I guess I should take that back. It is a unique solution, but it's the only one you got. Okay? And it's not very exciting. Okay? So x equals 0 is the solution. It's the only solution. Finally, let's do the last thing we're going to do here. Let's erase. And we'll have x of pi halves is equal to 1. Okay? I think that one still works. This is the one we change. Okay. X of pi halves is equal to 1 now, not 0. Now, the first one, when you plug in x equals 0, you see that C1 equals 0. I just didn't change anything there. That's it. So in the second one, when x is equal to, and this is pi halves, that's what I had there. I couldn't remember why I had a gap there. This is C1 cosine, and what is 4 times pi halves? 2 pi plus C2 sine 2 pi, and we want that to be equal to 1. Okay? What is cosine 2 pi? That's 1. So this will be a C1. Sine of 2 pi? 0. So we have C1 is equal to 1. Whoops. Whoops. The first boundary condition said C1 was equal to 0. The second boundary condition told you C1 was equal to 1. That can't be. Okay, you can't have the same parameter equaling two different values. So this obviously has no solutions. You cannot make that to work if those are your boundary conditions. So boundary value problems don't act like initial value problems. Sometimes they may work out fine, but other times, no, they don't work out fine at all. Either you have infinite number of solutions or no solution whatsoever. Okay? So, that was 4.1.2. 4.1.1. And that title was Initial Value and Boundary Value Problems. 4.1.2 looks like something we've seen before. Homogeneous equations. Now, I know that at least one person has paused to take a break. Do any of you need to take a break? We've been going at it for more than an hour. Let's do a quick break here. I need to. All right, we're back, and the projector's almost back. 4.1.2, the title is Homogeneous Equations. And before I tell you what this one is, I'm sorry, that was Warren coming down the hall. Just backing up, the word homogeneous in this context does not refer to the coefficients that are homogeneous functions in section 2.5. So we use the same term for two totally different things. But hopefully the context will let you know which one we're talking about. And here's the context in which we're talking this. We're talking about linear, nth order differential equations, and you've seen this form before. A sub n of x, d, the nth derivative of y with respect to x to the nth time, plus a sub n minus 1 of x, the n minus first derivative of y with respect to x to the n minus 1, plus a sub n minus 2 times the n minus second derivative. Yeah, I can't write. Got too crowded. The n minus second derivative of y with respect to x to the n minus second, plus dot dot dot, please, okay, plus a sub, let's start with 3 of x, and I forgot to put my x in this one, okay, d third y, the third derivative of y with respect to x cubed, plus a sub 2 of x. Oh boy, let me not include that one there. Let's pick that up on the next line. A sub 2 of x, second derivative of y with respect to x squared, plus a sub 1 of x, y dy dx, plus a sub 0 of x, y, okay, equal to, now if I put a g of x there, that's the one we started off in this chapter on, right? This time it's not a g of x, that g of x is a 0, okay? That is now what we're calling a homogeneous equation, okay? Whereas if this, all that up there was equal g of x, then this would be a non-homogeneous differential equation, linear differential equation. Now, I put a dash, they don't. They write that as one word. I think most spell checks will tell you that's not a word, but we don't have spell check. So, now, here's a very, okay, that's what we mean. If something's equal to 0, we call it homogeneous now. That's not what we meant back in 2.15. That was if your coefficients were, your powers of your coefficients were the same. The degree of the polynomials in each of your things were the same. Totally different things. So let's look at a couple and see, just for familiarity's sake. 2y prime, 2y double prime, plus 3y prime minus 5y is equal to 0. Homogeneous, non-homogeneous? That is homogeneous. Okay? Homogeneous. Okay? And we saw something very similar to that before. Here's another one. Why didn't they use the same thing? But they didn't. X cubed, y triple prime, plus 6y prime plus 10y equal e to the x. What's that? Non-homogeneous. Okay. Now, the fact they had variables in the coefficients, that has nothing to do with it. If you put a 0 there, that would be homogeneous. If you put an e to the x up there, that would be non-homogeneous, okay? The simplicity or complexity of whatever's on the left has absolutely nothing to do with the homogeneity. It's whether it's a 0 or not, okay? That's what makes it homogeneous as opposed to non-homogeneous. Okay. Now, what we're going to get to in a little while, not too much longer, is in order to solve that differential equation, that third order linear differential equations, you first got to solve this with a 0 in it, the homogeneous case. Then we'll proceed to do the non-homogeneous case. And that's the main reason we're bringing this up now. In order to solve this one, you can just, well, put you on the spot. Hurry, can you solve this one?
The first one?
Yeah. What is it? Anybody? What is it? The one that you picked out before. Identify. Oh, no, I'm sorry. Yeah, there are more solutions. If this had initial values that were all equal to 0, then that would be y is equal to 0. That would be the only solution. But because this, everything else fits, this has to be the only solution. That is the only solution. Y is equal to 0, right? Because this fits the criteria of that theorem we did earlier, that if these are continuous functions, that's a continuous function, then there's one and only one solution. And that solution has to be y is equal to 0. Okay. So we know that, okay, whether we realize it or not. Now, if that was equal to something else, then we can play around with it and get other solutions. But with that equals 0, that's one and only. This one, however, no amount of playing around is going to give it to you until we first deal with the homogeneous case and find solutions there, and then we'll do something else for that non-homogeneity. Okay, we'll get there in a bit. We must first deal with the, if you put a 0 in there, we call that the associated homogeneous equation. Okay. When you put a 0 in instead, do that. And that's what we're going to do first. Solve for the homogeneous case, and then go back and figure out what to do about that non-homogeneity. Okay. Now, it says remember these two assumptions. The coefficient functions, and that first one will be 2, 3, and 5, negative 5, they have to be continuous, and they are. And G has to be continuous. And in the top one, 0 is continuous. Okay, that's fine. And the second one, x squared is continuous, 6 is continuous, 10 is continuous, and e to the x is continuous. So both of those have to be the case. Now, the second condition, that a sub n of x cannot equal 0 for every x in the interval. The top one, no problem. 2 is not ever equal to 0. In the second one, though, possible problems. You cannot have an interval on which this is 0. So that means your intervals that you deal with here would have to never contain the origin. X equals 0. Can't happen, okay? 1 to 17 would be fine, or negative 3 to negative 1.5 would be fine. But you can't have negative 3 to negative 5, positive 5. because that would contain a 0 for your coefficient. Okay? So, remember those. Now, they're going to introduce something else that's fine for them to introduce. I just don't know why they picked this as the time to do it. There sort of is a reason, but it just seems kind of crazy. Well, almost unnecessary. In calculus, differentiation often is denoted by the capital letter D. In other words, make sure I write this the same way they do. Yeah. dy dx, they would express as dy. Okay? They would let those two things be the same. Now, one, to me it's not minor, but I guess they consider it a minor thing. With that d being just a d, you have no idea what the independent variable is. This tells you, y is the dependent variable, x is the independent variable. It's obvious, it has to be. This doesn't. But then on the other hand, y prime didn't tell you what the independent variable was either. So this is just as obscure as this. And we were happy with that. There we wrote it down in both of those examples. We just assumed it was with respect to x. Especially since this one had x's in it, then it would almost have to be. That one, there were no x's listed, so it could have been a t or anything else. By the way, the independent variable is often a dummy variable anyway, so it's okay not to know it. So this is the same as that, okay? And that. All three are the same, okay? It's called, D is now called a differential operator, okay? It transforms a differential function into another function, okay? So, yeah, I know why they're doing it now. What would be d of cosine for x, I believe it is, yeah. I'll make sure I did the right dummy variable. What would that be? Remember that d means derivative with respect to. A little louder? Okay, I know a sign is involved. 4x and what? Okay, you're integrating, I think. Derivative. 4 in front. Negative. Okay. Feel like a dentist here. Okay. Negative for sine 4x. Okay? Because the derivative of cosine 4x is negative 4 times the sine of 4x. Very good. Just to get an idea, yeah, it's stuff you've already done before. Okay, how about this one? D of 5x cubed minus 6x squared. What would that be? 15x squared minus 12x, yeah. It's just another way of writing it you're probably not used to, but it's pretty straightforward how to do it, okay? Now, higher order derivatives can be expressed in terms of d in the natural manner. Let me start on the clean page. I should have started earlier. I just didn't think about it. Okay. D by dx of dy dx is equal to d2y dx squared. Remember, that's that notation. What you reckon it would be in this new notation? Well, d by dx is d, and this would be dy, right? So d of dy, and what would be the logical thing to make that? D squared y. Okay. Time out a moment here. That looks like a square. Well, you know what? These look like squares too, but they're really not. They are indicating orders of derivatives. They're not squared. We'll call this by dx squared. It's really not a square, anything to do with it. That's not a square because d is an operator, okay? And you're raising that to mean you use the operator 2 times in a row. Just like squaring the numbers and multiplying twice in a row, okay? So, yeah, and we'll call it d squared y, but in reality, it's not really a square. It's just that operator used twice in a row. But it's okay. You can think of it that way. So in general, what we have been calling d n y dx to the n, what would that be in this new notation? D to the nth y. Perfect. Okay? That's what we mean by that. Okay? Now, I've been saying it doesn't mean the same thing, but we're going to almost treat it as if it means the same thing. Okay? Now, of course, y has to be a function you can differentiate n times. Otherwise, that doesn't make any sense. Okay? Now, you can have polynomial expressions involving d, such as this. D plus 3. What do you reckon that means? Let's say you had d plus 3 of y. That would be dy dx, assuming it's x, plus 3y. That's exactly what it means. D operating on y plus 3 operating on y. In other words, this is a little bizarre, but it's true. This is an operation on y. D is an operator. 3 is a number. So this 3 times y. That is a time. Okay, this is an operator. So it's a little strange, but it's indeed what you would expect it would be. Okay? Now, how about this one? D2, I'll call it d squared plus 3d minus 4. What if that were operating on, say, let's not use t. Let's use z. Okay, just so you know it doesn't have to be the same thing. What would that mean? D, it would be second derivative of z with respect to whatever your independent variable would be. That could be t, it could be x, it could be anything. So let's just call it x. Okay, we'll put x squared there, though that's not really squaring anything. Plus 3 times the derivative of z. Why is that there in the way? Z with respect to x is what we decided. Next, minus 4z. Exactly. That's exactly what that means. Okay? And then you can even mix it up even worse, like this. 5x cubed d3 minus 6x squared d2, I like to call them, that, plus 4xd plus 9. Okay, that's an operator, and we call these polynomial operators, so they just look like polynomials, but indeed they're going to act a lot like polynomials too. If that was operating, say, on y, we'll go back to y, that would be 5x cubed, the third derivative of y with respect to x cubed, even though that's not really anything being cubed, minus 6x squared. And by the way, I don't know why their example is like this, but these numbers don't have to be the same. That could be a cube, a squared, it could be a 15th power. That could be a first or a third power. This could be a second, or a 15th power, You don't have to have this matching that. Now, I don't know why their example they did, but it just happens to be that's what they use. And this would be second derivative of y with respect to x twice, plus 4x times derivative of y with respect to x, plus 9y. That's what that means. That's what it represents. Okay? These are all derivative operators. This is just a multiplication. Okay. That makes sense? Now, throwing that in there now is fine. Okay? Those are differential operators. In general, we define an nth order differential operator or a polynomial operator. Now here, and they love doing this, and I think there is some minor value in it, but it seems like they're just piling on one thing on top of the other. They're now going to develop a new operator, okay? And by the way, that L usually stands for linear, and that's going to be a sub n of x d to the n plus a sub n minus 1 of x d to the n minus 1 plus a sub n minus 2 of x d to the n minus 2 plus dot 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 all the way down to a sub 3 of x d3 plus a sub 2 of x d2 plus a sub 1 of x d, just d, you don't have to put a 1 there, plus a sub 0 of x. Okay? Yeah. Now, guess what that operator does? This L operator that contains the D operators. Does it look at all familiar? These are exactly what all you have to do is, instead of this D, put little d to the n over dx squared. Put a y there, and a y there, and a y there, and a y there, y everywhere on each term, and what you have is that first form that we had when we started talking about this pages ago. That's our general nth order linear differential equation operator. Okay? They just call it L for linear. Okay? So, now, I don't know if you remember the two basic properties of differentiation, and those would be, one, that a derivative of a scalar, c, times a function is the c times the derivative of the function. Remember? Okay? And the second being derivative of the sum of two functions is the sum of the derivatives of the two functions. By the way, those are sometimes called your linear operators for whatever, whether it's derivatives or other things. Okay? And I'll express those again here this way. D of c times f of x is c times d f of x, where d is your operator, your differential operator, and you just pull the c on the outside, and the other being d of f of x plus g of x is df of x plus dg x. In other words, the derivative of the sum is the sum of the derivatives. Okay? The derivative of a constant times the function is the constant times the derivative of the function. Those are called our linear conditions, you might say. Okay? So, that linear operator L, okay, that we just mentioned there, operating on a linear combinations of two differential functions, you've got so many linears in here, it's almost crazy, produces this. And again, this is so much nomenclature that really, I don't see why they get it. It's all true, absolutely true. The linear operator of alpha of x plus beta g of x, okay? This is basically combining those two operations together. This is alpha L of alpha of x plus beta L of g of x. Okay. Yeah. Now, remembering that this L stands for that huge thing up there, right? Huge, you know, that thing there, okay? So this operating, that whole thing operating on this would be alpha times that whole thing operating on just the F plus beta times that whole thing operating on the G of X. The advantage of this is just shorthand. It keeps you from having to write all that stuff all the time, and it keeps it in a simpler looking form. Things haven't gotten any easier, you're just writing it in an easier form. Easier to do form. Takes one line rather than 2 or 3 or 4 lines to get it all out there. Okay. Now, whenever this is the case, okay, in whatever you're dealing with, whatever operator you're dealing with, whether it's D or L or any other operator, if it fits this criteria here, it's called a linear operator. And L is a linear operator, which is why we call it L. Okay. Now, any linear differential equation can be expressed in terms of the D notation. Okay? So I think I'm going to start on a clean page here. And again, I'd rather be solving a differential equation than introducing all this way of talking about them, and then we're hardly going to use them again, but if they do show up, you hopefully will remember what they are. Here's a differential equation. Y double prime plus 5y prime plus 6y is equal to 5x minus 3. Okay? That is a linear second order differential equation. Okay? Non-homogeneous, by the way. Okay. Now, you tell me how to write that in D notation. D2y equal 5x minus 3. All right. Now, in sort of that polynomial, how could that be broken down? Plus 5d. Next. Okay. What you're doing, you're factoring out the y and writing everything else. D2, yeah, plus 6, y equal 5x minus 3. Okay. Now, that was what they asked for, D notation. I just took it one more step. Okay? Now, they did too, by the way. Okay. Now, if you wanted to, and for the life of me, I don't know why they're doing this, this is the non-homogeneous equation, what would be its associated homogeneous equation? Yeah, this thing would equal 0. Now, you could take it one more step and call that the linear operator y is equal to 0, and then the non-homogeneous part would be L of y is equal to 5x minus 3. Okay? And they usually put these in parentheses because those are operators. Okay? And again, why in the world bring all this up now? I'm not sure we're going to be using it. But that's just a way we can express it. Now, new subject. Related but not the same. In the next theorem, we see that the sum or superposition of two or more solutions of a homogeneous linear equation is also a solution. So that's something sort of new now. I think I'll go to a clean page to do it. Okay? Remember, if we have a differential equation, we may have an infinite number of solutions. Remember? As long as it's not an initial value problem, you could have an infinite number of solutions. So for a while now, we're going to be dealing with these. Let y1, y2, y3, comma, dot, 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 up to and including y sub n, I think they'll use k here. Y sub k be solutions for the homogeneous nth order differential equation 6. Be solutions for the nth order linear differential equation. And that's the one with that we've been writing all along. A sub n to x dn by dx to the nth plus, and you have all those terms there. This is just a short way of saying these are k solutions for that nth order linear differential equation. Okay? On some interval I. On some interval I. Okay? Now, here's the conclusion. If that's the case, if all these are k of the infinite number of solutions, here's another solution. Y is equal to C1, Y1 plus C2, Y2 plus C3, Y3 plus dot, dot, dot plus C sub k, Y sub k. This is also a solution. Okay? If you know you have 3 solutions out there, then any linear combination of those solutions is going to be a solution. Okay? Of a 6th order differential equation or whatever. Okay? This is called the superposition principle. Okay? Now, the ones up there are just designating these are different solutions, unique solutions. That has nothing to do with values or anything, it's just separate. The ones down here says this is the coefficient that goes with that one, this is the coefficient that goes with that one. These are just markers. Those numbers don't mean anything except saying this coefficient goes with that solution. Okay. Now this is true where introducing a new subscript, C sub I, okay, where I is 1, 2, 3, dot, 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 up to k, okay, obviously only goes there, are arbitrary constants. Not fixed constants, arbitrary constants, okay? And that makes y also a solution. Y also a solution. Okay? Not only do you have a whole bunch of solutions here that you know are solutions, then by introducing these, and these are not fixed c's here. These are arbitrary. So they could be any kind of values there. but C1, Y1 plus C2, Y2 plus C2. These are arbitrary constants. Okay? This is obviously represents an infinite number of solutions. If these C's could be anything, you have so many Y's there, boy, you have an awful lot of potential solutions. Okay? Now, here's a couple corollaries to that theorem. I think this is all we're going to have time for today. Okay? Here's the first corollary. They call it A. A constant multiple, y is equal to C1, Y1 of X, is a solution of a solution. I was going to say that doesn't make any sense. Of a solution, Y1 of X, okay, of a homogeneous linear differential equation of a, now these are homogeneous. Now they've snuck this back in here. Homogeneous linear differential equation is also a solution. Okay? So if you have a solution, Y1, you know it's the solution of that homogeneous linear differential equation. Any constant multiple of that is also a solution of that linear homogeneous differential equation. Here's the second corollary. A homogeneous linear differential equation always possesses the trivial solution. Okay? Because guess what? Now, I was going to say this before, but I held off when I said this could be, if Y1 is a solution, then C1Y1 is also a solution. What if that C1 is equal to 0? Then that produces the trivial solution. So the homogeneous linear differential equation always possesses the trivial solution as one of its infinite number of solutions. Okay, I think that just about ended what we have time for today. Let me see if I can make a minor adjustment here. We'll start next time with example 4 on page 123. Let's see about some homework exercises. This is a long section. 4.1.1. Okay, initial and boundary value problems. Do it either 1 or 3 or both, 5 or 7 or both, do number 9, do number 11, and do number 13. And then stop there because 15 starts talking about linearly independent. We haven't defined that yet. So stop at 13. We will pick up in 4.1.2 next time. Okay. Hopefully we'll finish 4.1.2 and 4.1.3 next time, though we may not. We'll see. And then move on to 4.2. Again, it's a little bit of a theoretical, very short section there, but then in 4.3 we actually start solving some, which I can't wait till we get there. Okay, good deal. Any questions? Good deal. We'll see you then on Tuesday. Have a good weekend. You just had a holiday, now you're going to have a weekend, so enjoy it.
You have a second test?
Oh, second test. If anyone did not get the second test, I do have copies of that. This covers chapter 2. Yeah, there it is. Who else needs one? Okay. Both of you get it last time? Both of you get the second test? Fine. You got it. me